then I have to break.
That's okay, so I think everybody's back. So let's continue with Tracy Slatryer, who's
Indirect detection, lecture 3. Yep, yeah. 3 of 5. So we're halfway through. Welcome back, everyone. So we're going to continue our discussion of indirect detection. So this was the plan that I gave at the beginning. So just as an update on where we are, we've talked in the last couple of lectures about the definition of indirect detection, about how to estimate the strength of indirect detection signals over cosmic history, and about dream and nightmare scenarios for indirect detection. And now we've moved on to the stage where we're calculating, okay, but if I have annihilations or decays or similar processes going on around us in the universe, what kind of observable signals would I actually see in detectors beyond the back of the envelope estimates? So we talked last time about the types of particles that could be produced, the types of standard model particles that are produced and the kinds of spectra of those particles that we would expect to see. So today we're going to talk about sort of the next step in the calculation, which is how do the particles that are produced by annihilation, how do the stable particles that are produced by annihilations or decays get from the origin point to our telescopes. Okay, and we're going to talk about this in two contexts. So the first is as charged particles propagate through our galaxy, they lose energy and diffuse through the galactic magnetic field, and that modifies the energy spectrum of particles that we observe at our detectors. Whereas for neutral particles like photons and neutrinos, especially at high energies, they don't get absorbed very much as they pass through the galaxy. And then we have directional information. And I want to talk about, what kind of spatial distribution of signals on the sky we expect to see in that case. So that's what we're going to do today. And if time permits at the end, I'll also talk a bit about the backgrounds relevant to different detection channels and targets, the indirect detection. And once we have all that together, then that should prepare us to go into the next lecture where I'll start talking about the current status of the field, about what observations are currently being done, what limits are being set with those observations, and so on. I also just want to mention, I think you should all have access to the PDF notes, the LaTeX notes that I sent out before the start. So I am generally following those notes, but there are examples in the notes that I'm not going to have time to get to in the lecture. So if something in the lecture was unclear, feel free to ask me questions at any points, but also take a look at the notes, see if they clarify it. And there are also some extra examples in the notes.
On that, maybe these are already available, but do we get these handwritten notes as well?
I can get you the handwritten notes.
Yeah.
But that's it. There might be, if there's a discrepancy between the handwritten notes and the PDF notes, usually the PDF notes will be correct. Although I have found a couple of typos in the PDF notes, so I'll be sending the organizers an updated version of that as well. Okay. I also will just mention briefly that the PDF notes do have some suggested exercises at the end of each section. Some of those exercises are fairly extended and involve things like, look up PPPC for DMID and figure out the spectra for these particles, figure out what the J factor would be from our galaxy. So, I do, if you have time, I think they're useful exercises. If you don't get a chance to do them until after the school, feel free to shoot me an email at some point in the future if you have questions about how to implement them. Okay. So where I want to begin today, and I'm also going to experiment with Tonya's innovation of using a chair here, which will hopefully make my handwriting better. Let's begin by talking about cosmic ray propagation. Actually, let's begin a little before that. So I said last time that when I'm thinking about dark matter annihilation or decay happens somewhere in the universe or in our galaxy, I said the step one last time was to go from the DM model to a spectrum of stable standard model particles. And we talked a bit about what those different stable standard model particles could be and how different standard model initial final states from the annihilation or decay would give you different spectra of stable standard model particles. So step two then is, once you have that spectrum of stable standard model particles, how does that translate into the signal that you actually see in your detector? And then step three is, how do you tell that signal apart from backgrounds? So we're going to focus mostly on step two today, somewhat on step three. So in category two, but also, somewhat in category three, since the backgrounds may also be charged particles that need to propagate, we need to understand how, if charged particles are produced in our universe, how do they get to our detectors? Okay, so the basic issue here is that charged particles being charged, if you have a magnetic field present, they don't travel in straight lines. If you have a turbulent magnetic field, then they will scatter off. Then they will scatter off the magnetic field and essentially diffuse through the magnetic field lines. Like if it's an ordered magnet, if the B field pointed in the same direction everywhere in the galaxy, then we could say, okay, this charged particle is just going to follow some helical path. But since the magnetic field is actually quite turbulent and random, what you get instead is like a diffusive random walk process through the galaxy. So charged particles diffuse through the galactic B field. Or more than galactic B field if they're coming to us from outside the galaxy. Now, simultaneously, while this evolution is happening, while the particles are bouncing around, scattering off the turbulent magnetic field, simultaneously they can undergo energy losses through various processes. So one source of those energy losses is just synchrotron radiation, which again comes from the magnetic field. As these charged particles pass through the magnetic field, they're accelerating, so they're going to radiate. But also there are other radiation fields in our galaxy. Our galaxy is full of stars, so we produce starlight and we have the cosmic microwave background radiation. So as these charged particles scatter off those radiation fields just through electron photon scattering or proton photon scattering, they're also going to lose energy to those processes. And turns out for protons, this loss rate is pretty slow, but for electrons, this loss rate is quite fast, and it's one of their major energy loss processes. So for electrons, we refer to this as inverse Compton scattering, electron cosmic rays. And I'm going to abbreviate that as ICS. So this is just, and this is also applies to positrons, same sign for high energy particles, they behave just the same. So this is just electron plus photon scattering, but if the electron comes in with a lot of energy and the photon comes in with a low energy, then at the end of the scattering, the electron will transfer energy to the photon. So this kicks the photon up to a higher energy, which could be in the X-rays or the gamma rays. The reason why this is called inverse Compton scattering, not Compton scattering, is traditional Compton scattering, the photon has more energy and the electron is at rest, but it's just a change of plane. Like that's all the inverse means. And let me actually change that from electron cosmic rays to electron positron cosmic rays. And the other kind of loss that can happen, although the time scale for this is typically longer, is that protons can collide. So proton CRs and antiproton CRs can collide just with protons in the gas and produce a shower of subsequent particles. So this is just a proton-proton collision or an anti-proton-proton collision. And that's a messy hadronic process and can produce a lot of secondary particles. So those secondary particles, it's somewhat like a hadronic dark matter annihilation, as we discussed last time. So this will produce, this can produce light neutral and charged pions, as well as heavier hadrons. And just as we discussed last time, these will give rise to secondary electrons, positrons, and photons.
Is there some threshold energy at which we consider something to be a cosmic ray?
Good. There probably is, but I don't know about it. In today's lecture, I'm going to be primarily thinking about relativistic cosmic rays.
Thanks.
Yeah, so I'll talk about this a bit more when we come to the studies. There's partly a practical reason for this, which is that low energy cosmic rays are quite hard to measure at the Earth because they get badly deflected by the solar wind. High energy particles can get into our solar system. Low energy particles often get deflected. But so there's a consequence of this is that the Voyager experiments launched in the 1970s, which are now out past the heliopause, actually provide our best measurements of low energy electron and positron spectra from the galaxy, because they're our only instruments that are out beyond, that are out beyond the heliopause. I was a little embarrassed a few years ago. I had set these cosmological constraints on annihilation and decay to light to electrons, and I was like, and there's no competition from cosmic ray experiments because you just don't see low energy particles like this. And then Boudard et al. Wrote a couple of papers where they were like, actually, this 1970s experiment gives better constraints than your fancy cosmological bounds over like 2/3 of the parameter space that we have. And I was like, beaten by Voyager, okay. But yeah, I mean, it was smart that they put a cosmic ray spectrometer on the Voyager missions when they sent them out. Because yeah, now we actually have a measurement of the interstellar cosmic ray spectrum of low energies, which would otherwise be very hard to get from that. So yeah, when I show you constraints next time, some of them will be from Voyager. So it's good to think ahead. Okay, so we need to model all these processes to understand both the signal and the background for charged particles produced through dark matter annihilation and decay. Typically, to do a real analysis for this, you use numerical tools. Like this is, I mean, you can do a back of the envelope estimate to get an estimate of how things work, and that's what we're going to do today. But for realistic applications, you use numerical tools to handle this propagation. So two of those tools are undoubtedly others, but one that's very long-standing and very well-known is called Galprop. Another one is called Dragon. The PPPC for DMID site that I mentioned yesterday also has some like pre-computed tables for propagation for specific cases. So what I'm going to try to do in this section of the lecture is I'm not going to teach you how to use these numerical tools. What I'm going to try to tell you instead is, what equations those tools are solving, what kinds of boundary conditions they're setting, and then I'm going to make a bunch of approximations so that we can talk about just the properties of the differential equations and qualitatively how this propagation affects the spectra of the particles. Okay, so this is not going to, so I'll tell you what they're solving, but this is going to be mostly back of the envelope. So I'll also say that the reference that I'm using for most of this is by one of the, or this is a review, this is an old review, but I think still largely valid, by one of the Galprop authors. Most of this analytic discussion is based on this review. So if you want to see more details, this is a good place to start. Okay, so our primary goal usually is to estimate the steady state energy spectra of the particles at some point. Okay, we're not typically interested in looking for transient signals, because if we're looking at dark matter annihilating or decaying in the halo of our galaxy, it's been annihilating or decaying for 1 billion years. Okay. So our primary goal is usually calculate steady state energy spectrum. So I'm going to define a quantity that I call psi, which is a function of the position of the cosmic. So this is going to be a cosmic ray density as a function of position, the momentum of the cosmic rays, and of time. Okay. And I'm going. Sorry, this is just going to be the differential number density of a particular species of cosmic rays with respect to energy. Okay. So I want to know the steady state value of this function throughout the galaxy, ideally, yeah.
Is this in a co-moving volume, or are we just dealing with the galaxy?
Good. So good. That's a good question. I'm going to ignore cosmological expansion effects for the purpose of this part of the lecture. Okay. But you could put in redshifting as well. So when I talk about J factors, I'll talk more about redshifting, but usually for I will tell you for the kinds of cosmic rays that we're measuring, like AMSO2, and the kinds of cosmic rays that are relevant to dark matter lighter than sort of tens of TeV, the path length for those cosmic rays generally stay in the galaxy. For electrons and positrons, we're probing volumes within, like for 100 GeV to TeV, positrons and electrons, we're probing volumes within about 1 kiloparsec. Our distance to the center of the galaxy is 8.5 kiloparsecs. For protons, we can probe larger volumes, but still the protons mostly sort of get confined inside. You can model our galaxy as a leaky box for the purpose of protons. The protons bounce around inside our galaxy many, many times before they escape or lose all their energy, but still we're largely probing protons that are produced in our galaxy until you get up to much higher energies. So yeah, so for the purpose of this, I'm ignoring redshifting, but it's a good question. Yeah, when we talk about photons and neutrinos, we will have to worry about redshifting because we do see photons and neutrinos from way outside our galaxy. Okay, so if I ask how does the evolution of this field behave, then the diffusion equation the equation that these numerical codes are solving looks like this, that the rate of change of this number density over time is going to be governed by some source term. So this is telling you about the injection of cosmic rays. And then we have a diffusion term governed by some diffusion coefficient. So this is telling us about spatial diffusion in the homogeneous field minus B. The general form of the equation also has this convection term in it. I should say, I'm going to write this down for you, but then I'm immediately going to take a simplified version of it for purposes of this lecture. So this is a diffusion coefficient. This is a convection velocity. You can have what's called a reacceleration process, which is basically diffusion in momentum space. So like interactions of particles with effects that can accelerate them, like passage through supernova shocks or something, and cause the particles to undergo a random walk in momentum space as well. So that, if that's present, you get this reacceleration term. Actually, sorry, I guess this could be like grad P squared dp. And then we can have a term just for the particles losing momentum as a function of time due to inverse Compton scattering or synchrotron or these other processes that we've talked about. It's another term here. Yeah, sorry, I guess this was originally written for just scalar P, but I guess more generally this is a grad. Yes. Okay. Sorry. Let me reframe that, because this was originally written for assuming no dependence on P, and I'm not sure that I have upgraded it to the vector version correctly. So let me just put that to this. It's not going to matter for the approximation that I make next anyway. Okay, so we have an equation that looks we have an equation that looks something like this. This piece is describing diffusive reacceleration. This is describing energy losses due to cooling. And these are the possibility that some of these particles are just decaying away or are striking the gas and disappearing into a shower of secondary particles. So the tau F is for fragmentation, and the tau R is just if these are unstable cosmic rays. So in general, this is the kind of equation that these codes are solving under the hood. In addition to this baseline equation, you need to set some boundary conditions. This is just a PDE. The sort of simplest form of the boundary condition is to just take some kind of free escape version at the boundaries of the galaxy. So the simplest version is we model the galaxy as a cylindrical slab. And we say outside the galaxy, these cosmic rays free stream away very effectively, and so their density effectively goes to 0. Okay. But you can also do more physical boundary conditions, like say there's some probability of escape at the edges. And you can do various levels of complexity in these equations. For example, this diffusion coefficient, this energy loss rate, they could depend on your position in the galaxy. They could have anisotropy, like they could depend on the direction of the direction the particles are traveling in. So, and people have written a number of papers basically starting from this equation and either adding additional terms or adding additional parameter dependencies. But for the purposes of today, what I want to do is look at a simplified version of this containing two of the terms that are usually thought to be most important and understand how the steady state solution in those circumstances is going to differ from the injected spectrum. Okay, so let's do, so the simplified version. I'm going to ignore convection. So that means I'm ignoring any kind of like winds that are bulk transporting cosmic rays through the galaxy. I'm going to ignore diffusive reacceleration. So there's no diffusion in momentum space, the only random walk-through in position space. I'm going to assume that I can ignore fragmentation for purposes of the calculation that I'm doing here. And I'm going to assume I'm only looking at stable cosmic rays. So I'm also going to ignore decay.
Yeah, so wait.
So I guess the effects of dark matter are implicitly assumed in the source term, right?
Yes, exactly. But so yeah, if I was so again, this is a calculation to figure out how all charged particles propagate through the galaxy because I need to apply this to both signal and background. But you're right. So my dark matter annihilation would serve as a contribution to Q.
Thank you.
Very good. I should also say that this is for diffusion through the galaxy. And when we need to think about cosmic rays striking our detectors at Earth, we live inside a solar system, not just a galaxy. And so the effect of having to travel through the solar wind and experience the sun's magnetic field can also modify the spectra. I'm not going to go into detail about solar modulation calculations, but I can point you to some calculations if you're interested.
Actually, I'm okay. Thank you.
Okay.
But we could just, those solar modulation, whatever, those could just be factored in.
These solar effects can just be factored into what we have here, right? Or is it something really different?
It's the same physical processes, like you're interacting with the magnetic field, but the magnetic field of the sun is pretty different from the magnetic field of the galaxy. So but both in shape and in magnitude. So typically people do those calculations separately, but it's also usually true that the solar modulation effects tend to die off pretty fast with energy, which you can see explicitly in AMSO2 data, because the sun goes through an 11-year cycle during which its magnetic field changes. And you can look at the cosmic ray spectrum move around over 11 years in AMSO2 data, because it's been up there for long enough now. And you can see that like the low energy end of the spectrum, just kind of let me draw it on here. So, you know, if you have a spectrum that looks something like this in AMSO2 data, you see that over multiple years, the low energy end of the spectrum moves around quite dramatically as you go through the solar cycle, but the high energy side is almost unaffected. So you can like directly measure the energy dependence. I think Mark was more of an expert on this than I am. So if you have questions about solar modulation, if you have questions about this, you will be a good person to answer. I have largely managed to avoid solar modulation calculations in my own work. So, okay, so let's look at looking at our simplified version. So I'm going to ignore all those terms and I'm going to focus on relativistic CRs. So I'm just going to set P equals to E. So I'm going to largely ignore the masses of my cosmic rays in this calculation. And I'm also going to assume that the diffusion coefficient and the energy loss rate, so these are my only two remaining terms in the equation, are only functions of energy. So I'm going to ignore any dependence that they may have on position in the galaxy or direction in which the particles are moving. Okay? Now, the numerical codes are not making all of these approximations. This is our theorist's approximation. Yeah.
Could you repeat again what that diffusion coefficient is?
I'm going to say a little bit more about that in a moment.
Okay.
So I may just, so the question was, can I say more about what the diffusion coefficient is? I'm going to say a little bit more about how that's modeled in one bit. But I mean, what it is describing is the properties of how particles of different energies interact with the turbulent magnetic field of the galaxy. And so what it depends on is the structure of the turbulent magnetic field on small scales. So, okay, so once you make all these simplifications, what you get is a version of the diffusion equation that looks like, I'm just going to call my dxx d of e at this point. So this is my energy dependent diffusion coefficient. This is multiplying, I can pull this out the front of the grad because it only depends on energy, not on position. And then I'm going to have an energy loss term, which I called P dot before. I'm now going to write that as B of E coefficient, psi, and I have my source term. So this is the energy loss rate, du dt, for one particular particle. Okay, so let's talk a little bit about the diffusion coefficient. So the typical simplest modeling of the diffusion coefficient, which I'm going to adopt here, is that it has a power law dependence on energy. Okay, so it has some baseline value. I'm going to take my calibration energy to just be 1 GeV here. And to match the data, you turn out to need a D naught around a few times 10 to the 28. Centimeters squared per second. Okay, so if we ask what is delta, the range of, so delta, you can read the review that I looked at earlier for some discussion of different models for delta, but it depends on the structure of, on the scale dependence of turbulence in the magnetic field. The typical range for delta that's usually considered is between about 0.3 and 0.7. But in reality, this is a parameter that we fit from observations of the cosmic rays. The latest, so there are some theoretical models for specific turbulent structures, which are called Kolmogorov type diffusion and Kragman type diffusion, which suggest respectively delta of 1/3 or 1/2. So. And I saw there was a question up there, but I'll just. So, yeah, I'm not going to go into these in detail, but if you want to look up these scenarios, these are the names that you should Google. And the recent data from AMSO2 suggests that delta should be in the range of about 0.4 to 0.5. So, a reference for this. However, even more recent data suggests that this simple power law model is probably too simple, and that in reality, some kind of broken power law model may be a better fit to the data. So, an example for that is 2103. This is generally me. There was a question up the back there.
Sorry, where do we get these equations in general? Are they somehow similar to the Navier-Stokes equations in hydrogen dynamics, or also is it a pure classical computation?
So, like, where do we get the diffusion equation?
I mean, these equations you were showing, right, before these longer equations, no, the ones before you did, this one. From where do we get this?
Yeah, so I mean, well, it is a hypothesis that cosmic rays are well described by this equation, but it appears to be fairly well justified by the data. But these are fluid equations essentially. They're assuming particles diffusing with some. So this is a So I mean, this term is just describing diffusion with some energy dependence. Where these other, I think these diffusion terms are basically describing, random walks in position space or in momentum space with some length scale that is set by the diffusion coefficient. The energy loss term is just saying, well, if particles lose energy at some rate, then that will reduce that will reduce their number density at a fixed energy. These are just decay terms. So there's nothing special about it being cosmic rays per se. This is not coming from quantum mechanics. So it's classical physics in that sense, but relativistic classical physics.
So we think this cosmic rays are somehow fluid, and we derive that from usual continuum mechanics, or
you're positing that the hypothesis is that as cosmic rays pass through the magnetic fields in the galaxy, there's a reasonable approximation how they behave. There are other correction terms that you can add for this, like when cosmic rays get dense enough, there are like back reaction effects, like the cosmic rays will modify the magnetic field and the medium that they're traveling through, and so then you have to add in additional effects. But so I mean, this is an empirical model, but you're basically just treating. But yeah, so I mean, if the question is, you may want to look up these references on like Kolmogorov diffusion and Kreitman diffusion, because these are both just saying, if I have charged particles propagating through some turbulent magnetic field, how will they diffuse? How will they travel over time?
Yeah, because they usually write these equations in terms of velocities of the particles.
So this is a relativistic one.
There's a question.
Yeah, so by assuming our diffusion coefficient is only a function of energy, are we basically saying we're going to ignore like local B field effects? And
yes. Yeah, so, and there's actually been really interesting experimental evidence recently that the diffusion coefficient, at least for electrons and positrons, is definitely not uniform throughout the galaxy, because we have observed pulsars that have gamma ray halos around them that we think come from high energy electrons and positrons streaming off the pulsar and undergoing this inverse Compton scattering process where just those high energy positrons and electrons scatter off low energy photons, upscatter them to gamma ray energies. And we see these TeV gamma ray halos around the pulsars. Now, of course, we knew this physical process was present, and we thought these pulsars might be creating high energy positrons and electrons, but nobody was expecting to see these halos, because if you use these standard estimates for the diffusion coefficient and you ask, okay, how far would these particles diffuse before they lose most of their energy, you find that they should have diffused all the way to the Earth and beyond, and consequently the halos should be spread out across a region of about 45 degrees on the sky, which would make them undetectable by the telescopes that were doing the searches. The Hawke telescope is what found these. But in fact, it turns out that the halo is only about 2 degrees wide. So that tells you, I mean, that tells you one of a couple of things. Like it could be that, you know, there's some strong magnetic field that's causing the particles to lose their energy much faster, but we have independent measurements of the magnetic fields around these pulsars. And they're like a much smaller region, like they can't explain this 2-degree fall off. So, so the current hypothesis is that there are zones of impeded diffusion around these pulsars. Yeah, due to the effects of the pulsars themselves. But this is still an area that people are trying to understand. But yeah, by assuming that this only depends on energy, I am basically treating the galaxy as a homogeneous cylindrical box where the only relevant scale is where is the boundary of the cosmic ray halo of the galaxy. And that's the only relevant distance scale in the problem. So, yeah. Okay, and we're about to use that in a moment. Okay. So let's taking this very simplified model, let's look at this PDE and say that we're interested in the steady state solution. So we're interested in d by dt equal to 0. So we're looking then for a solution to some given source term. We're interested in looking for a solution to this equation. So the only length scale in this problem as expressed here, I mean, so there could be a length scale introduced by the source distribution, but you know, I could imagine, you know, a mostly like homogeneous source distribution here. In that case, the only length scale will be introduced by the boundary conditions. Okay. So let's say that there is a length scale R fixed by boundary conditions. Again, in a realistic scenario, you'd actually like just go ahead and solve this differential equation. I'm not going to do that. I'm trying to sort of sketch the behavior of this differential equation for you. So, okay, if I say there's a length scale R, so it's fixed by the boundary conditions, and I ask, all right, what is grad squared of phi? What is grad squared of the solution of this equation? Parametrically, by dimensional analysis, it's going to be something like phi divided by R squared. Okay. I'm going to put a minus sign in here because I'm assuming that the density is higher in the center and it falls off towards the boundaries. This is a tilde. There will definitely be prefactors in any realistic model, just saying that by dimensional analysis, there has to be some kind of scaling that is like 1 over R squared. But again, this is all rough estimate to look at the properties of the equation. Don't take it too seriously. Okay. Now, what about the energy spectrum? I'm going to consider 2 types of energy spectra to give you examples of how this would behave. So, case 1, let's first consider a power law type energy spectra. The other case I'm going to consider is a Della function. So this gives you sort of a view of what happens to smooth spectra and what happens to very peaky spectra. So let's say that let's say that we have a power law energy spectra that looks something like phi goes like e to the minus alpha, some alpha. Then when we ask what is the derivative, and I'm going to assume then if I ask, you know, parametrically, what is d by d, d of e times phi, we can guess that this derivative with respect to E acting on a power law is basically going to give us a power of 1 over E. Okay. So if under these very sort of loose dimensional analysis approximations for how things should scale, then I can say that the steady state solution should roughly satisfy an algebraic equation, not a differential equation, which looks like have this diffusion term, have this loss term times phi should be about equal to Q. Now let's understand, you know, what's going on here physically a little bit more. So these 2 terms here, d of e over r squared and b of e over e, these both have units of inverse time. So let's define these as giving us some time scales. We'll say that the time scale for diffusion is parametrically R² over dV, and the time scale for cooling or energy loss is parametrically going to be E. Again, this is basically just dimensional analysis. Okay, like I'm not doing anything more deep or intricate with dimensional analysis here. Okay, so then I can write my steady state solution as being approximately given by just Q divided by 1 over tau diff plus 1 over tau loss. So roughly speaking, this is going to be in 2 regimes. If the timescale for diffusion is much shorter than the timescale for losses, then this is going to be completely dominated by the 1 over tau diff term. I'm just going to get Q times tau diff. If the opposite is true, then I'm basically going to just be replacing the source term Q by the typical timescale for loss. Okay, so all this is saying is, to a crude first approximation, there's a timescale for diffusion, there's a timescale for losses. I take whatever my injected rate of particles per unit time is, I multiply by the appropriate timescale. That gives me roughly the steady state distribution of particles. Yes. Thanks. Okay. Okay. So when we ask how the energy spectrum of phi is going to differ from the energy spectrum of Q, what we care about is how these relevant timescales depend on energy. Okay. So I mean, just again to say what's physically going on here, what this diffusion is saying is if particles at different energies diffuse at different rates, and you source the particles at some point inwards to the galaxy and then they flow out towards the outskirts of the galaxy, then that's going to give you a change in the energy spectrum. Because at any point in the galaxy, you know, the higher energy particles, you'll be looking at higher, if you look at higher energy particles versus lower energy particles, you are looking at particles that have diffused a different, that have been diffusing for a different amount of time since their origin point. So that's why, even though the diffusion is, you know, the same and homogeneous everywhere, if you have an inhomogeneous source term or inhomogeneous boundary conditions, it's going to induce an energy dependence in the spectrum of the particles that you look at. So now whichever of these timescales is shorter, diffusion or loss is going to dominate that evolution in the spectrum. So let's look at these 2 regimes. So the first regime, which is the diffusion dominated regime. So this is the first one, timescale for diffusion is short compared to the other timescales in the problem. So in that case, the energy dependence just comes entirely from the energy dependence of the diffusion coefficient. Yeah.
I might have missed this, but is there some reason to assume that there's going to be a big separation in these 2 timescales?
No. Well, okay. In practice, for protons and antiprotons, there is a big separation in the 2 timescales. Like you can work them out, but yeah, I mean it depends on the magnetic field of the galaxy and how it compares to the timescales for ICS and synchrotron. It turns out that for protons and antiprotons in the energies that we look at, usually the diffusion timescale is shorter than the loss timescale. So there's the statement that protons diffuse around the galaxy and bounce around the galaxy many, many times before losing all their energy to loss processes. So protons and antiprotons are generally diffusion dominated. But for electrons and positrons, it's not so clear. Like for them, the timescales are much more comparable. So it depends on what specific cosmic ray species you're looking at. And there's not, in general, as far as I know, a reason to expect a big separation. It's a good question. But you know, this is we think one of the reasons why electron and proton cosmic rays have quite different spectra at the Earth, because the processes that modify their energy spectra differ. Okay, so in this case, we've said phi is roughly speaking going to be given by the injection rate times the diffusion timescale. The diffusion timescale, so this is Q R² over d of E. So the energy dependence is coming from d of E. We said the d of E goes like e to the delta. So this is going to be whatever the energy dependence of the injection is times e to the minus delta. So the effect of diffusion in this case is to take whatever energy spectrum your injected particles have and tilt it by a factor of e to the minus delta. So reducing the number of high energy particles relative to low energy particles. So when we reduce the number of high energy particles and increase the number of low energy particles, we call it softening the spectrum. The reverse we call hardening the spectrum. Okay, so just as an example, the observed spectrum of protons at the Earth has an index. This is not from dark matter annihilation. This is from the backgrounds, has an index which is about e to the minus 2.7. So the injected spectrum for these protons is thought to come from acceleration of the protons in shocks surrounding supernovae. If those shocks are strong and supersonic, there's a general prediction that the injection spectrum should be about e to the minus 2. So if that was fully true, if we were in that limit, that would give us an expectation of about delta of 0.7, which is indeed what earlier data suggested. The newer data suggests that there's a bit more going on than this simple diffusion model, and you want more like delta of 0.5. But that's parametrically where we are. So you can see, even this even this very simple picture allows you to sort of see what, why from a model of what the injection spectrum was and from observations made at Earth, we can try to make inferences about the diffusion coefficient. What actually is done is that people look at the properties of a large range of energy spectra for cosmic rays and to try to extract this information. And AMSO2 observes like mostly power law spectra, but there are breaks in the power law as specific energies, which may be telling you about modifications to the diffusion coefficient scaling of those energies. Okay, so what happens? So in the loss dominated regime, what we need to know about is how the rate of energy loss varies as a function of energy. So this is relevant for high energy electrons and positrons. So if we ask what are the main energy losses for electrons and positrons, they're synchrotron radiation and ICS, as we discussed earlier. So we can ask how those processes vary as a function of energy. And this is just electron-proton interaction. So we understand these reasonably well. So synchrotron, you can work it out, and you find that the rate of energy loss to synchrotron per unit time for a particle, for a charged particle in a magnetic field scales as e squared. Higher energy particles lose their energy more efficiently than synchrotron. ICS, there's also d dt is proportional to e squared in what's called the Thomson regime, which basically holds provided that the energy of the incoming electron times the energy of the incoming photon is smaller than the electron mass squared. When that's not true anymore, so when you have like sufficiently high energy incoming electrons, then you instead break into the Klein-Machina regime, which gives you a different energy scaling. So we expect to see a break in the spectrum of sufficiently high energy electrons and positrons corresponding to that scaling. But for the moment, let's just assume we're in the Thomson regime. But just as an example, starlight in the galaxy is about 1 eV in energy. The mass of an electron is half of 10 to the 6 eV. So in order for the electron energy times the photon energy to be smaller than me squared, that holds up to about a few hundred GeV electrons. So long as we're below a few hundred GeV electrons, this Thomson regime is usually a pretty good approximation. So for now, let's assume this, because in this case, our scaling result is very simple. B of E is proportional to E squared. Higher energy particles lose their energy faster. So if we ask the timescale for loss is then just E divided by B of E. So this is going to be proportional approximately to 1 over E. So again, that tells us, so the steady state spectrum in this case is the injection spectrum times the timescale for loss. So again, we see, let's put a proportionality symbol there. So again, we see that the spectrum we expect to be softer in this cooling dominated regime, but instead of depending on delta, it's now just a flat index change of 1. Okay, so what we see here is because delta is less than 1, the softening is more pronounced in the loss dominated case compared to the diffusion dominated case. So what we expect here is, okay, so tau loss and tau, so the thing you're going to note here is that tau loss and tau diff both fall with energy, but tau loss falls faster, at least in this case for electrons and positrons. Since the shorter time scale is what dominates, that means that higher energy particles are increasingly going to be in this loss dominated regime or cooling dominated regime. So what we expect for high energy electrons is that at low energies, they might be diffusion dominated, but at high energies, it's eventually going to become cooling or loss dominated. And at that point, we expect to see a change in the slope of the spectrum. Okay. So just these propagation effects can give you features in the spectrum that have nothing to do with the underlying particle physics. Okay, so if we think question there?
Oh yeah, thanks. I think I maybe lost you a little bit. So,
Yeah,
so
sure.
the loss dominated regime reduces the number of high energy particles more efficiently, basically, than the
Yeah.
diffusion dominated.
Yeah.
So why is that more important for high energy particles? Wouldn't there be fewer?
Good. Yeah. So high energy income. So suppose I have an electron that's flying through the galaxy. It has some initial energy that I've injected it with, like maybe my dark matter particles annihilated and made 1 TeV electron. Okay, so then the first thing I want to know is, okay, like what? So how is this particle? How is this particle going to evolve? So what I'm saying is that if I ask what is the time scale for this particle to lose, an e-fold of its energy through inverse Compton scattering of synchrotron on one hand, or through so okay, I guess diffusion is a little bit complicated when I'm just talking about one particle, but so if I have so this particle is losing energy through losses. That means that if I inject more of these particles at different times, they will make a whole spectrum. Particles will actually do the case of delta function injection in a second, because it's a little bit different. So at the same time, if I look at a particular point in space, diffusion is softening the spectrum because the high energy particles are moving out faster than the low energy particles. But I can ask you, which of these effects dominate? Like, is it more important that this particle is, is this particle more likely to lose half its energy first by inverse Compton scattering or synchrotron, or by, some of the particles of this energy have escaped? And the answer is that increasingly, as you go to higher energies, it's the loss to the inverse Compton and synchrotron that will become more important, because that time scale scales faster with energy. Okay, so that's the statement. And so then what you expect is, so when you're looking at a power law spectrum, the effect of those losses is to tilt the spectrum by e to the -1. The effect of the energy dependence of diffusion is to tilt it by e to the minus delta. So then what you expect is a spectrum which is Q of E times e to the minus delta up to some energy, and then a transition to Q of E times e to the -1 behavior at higher energy where the losses take over. Okay? And you could actually use the present, if you're sure that there's not a sort of underlying break in Q of E at that point, you could use the position of that break to diagnose when losses change to diffusion, which tells you something about like, what the diffusion coefficient is. If the break's in the energy range that you can see. And if you're sure that it's not, so I mean, the question of, are we looking at a change in the source spectrum or a change or a change in the or something like this about the propagation parameters is often a question that doesn't have a very obvious answer. Okay, so that's what I wanted to, so that's what I wanted to say about that. Let me just do one other example where instead we had, where instead of injecting a power law energy spectrum, which is what we assume to get this V of E over E approximation, suppose that instead I just inject some particles at a fixed energy, so like a delta function energy injection. So let's say this injection rate is some injection rate times delta E minus MdM. So I'm injecting electrons at the energy of the dark matter mass. Okay, so this is an example from dark matter annihilation. So then, and then let's look at what would happen in the cooling dominated regime for this case. Then if I drop the diffusion term, the steady state equation going back to the original differential equation looks like this. So then, you know, I can just so I can integrate this directly. So in this case, and this we know scales as something proportional to E squared. So if I solve this equation instead of just doing the dimensional analysis arguments that I gave earlier, what I would find is that phi of E equals Q naught over V of E times a step function. Okay, so this is where instead of just using dimensional analysis to say that this derivative with respect to E should just be a 1 over E factor more or less, I'm actually integrating this equation. So in this case, what you would find is that the spectrum of the injected particles just scales like an e to the minus 2 spectrum in DNDE, but then up to some sharp cutoff. So the diagnostic of a delta function injection of electrons, like you will not see that spike of electrons at your detector. What you will see instead is a power law distribution of electrons that has a sharp cutoff. It looked like, was there a question there maybe?
Is cooling dominated, loss dominated?
Yes,
here?
cooling, yes, loss / cooling dominated regime. Thank you for checking. Yeah. So this, all I'm saying here is let me just throw out the diffusion term and just look at how an ejected particle evolves under losses. So in that case, so the point that I want to make here is just these propagation effects transform. Like if you think of sort of the Green's function of if I inject a delta function, what happens to it? The answer is it becomes a power law with a cutoff. So this is why it's often a good approximation to treat your cosmic ray spectra as detectors as power laws, possibly with cutoffs. Because even if you inject particles that are monochromatic in energy, they will get converted through the steady state spectrum will end up being a power law with a cutoff. Okay. The one other thing that I want to say about cosmic rays is that we can also use this simple example to think about the case where cosmic rays are produced as secondaries from some other interaction. So let me give you an example. We would like to be able to look for positrons produced by dark matter annihilation, okay? Right? This is one of the channels that we might use to search for dark matter. So then we need to think about what are the astrophysical backgrounds for positrons. You know, you might say, oh, well, there's hardly any antimatter in the universe, so maybe there are basically no astrophysical backgrounds for positrons. That would be very nice, but it is not the case. So where do most positrons in our galaxy come from? We think that most positrons in our galaxy are produced when protons collide with the gas. So this process that I talked about that I talked about way up here. The high energy proton cosmic rays collide with the gas. They make a whole bunch of secondary particles, and those secondary particles can include positrons. So then we might want to say, okay, so what is the spectrum of those particles going to look like, of those secondary positrons? And so now, rather than having Q of E be some kind of injection from dark matter annihilation or decay, or some injection from supernovae, we can say that Q of E is the spectrum of the original protons. Okay? Or well, it's the spectrum of the positrons produced by protons hitting the gas. So that's our new source of secondary particles. So what happens when we get particles that are produced as a result of, that are produced as secondaries from other particles that have already experienced cooling or diffusion? The effect is you basically get to stack up these softening effects from cooling or diffusion. So secondaries. So in the numerical codes that I've been discussing, what this means is that you have additional differential equations for these secondaries, and you have coupled differential equations, so that the terms describing losses of the original primary particles to these collisions translate into source terms for the production of the secondary particles. But let's just take as an estimate, let our steady state primary distribution serve as the source distribution Q for the secondary particles. So we're going to just assume that Q is proportional to the primary, to the steady state spectrum of the primary particles. So then let's let's take an example. E.g., suppose that we have some source of protons in the galaxy that has with Q of E proportional to e to the -2. So this could be acceleration in the shock surrounding supernovae. So then the proton steady state spectrum, and we'll assume it's in the diffusion dominated regime. As we discussed earlier, phi is going to be proportional to e to the -2 plus delta. It's going to get softened by a factor of diffusion. But so then for the positron secondaries, we can approximate things as E plus have Q of E proportional to e to the -2 plus delta. Okay, question?
This might not be important, but where does that 2 come from?
So I'm just positing, like, where does the Q of E proportional to e to the -2 come from? So the way we think that most cosmic rays get accelerated in our galaxy is that when stars go supernova and explode, there is a rapid expanding shock around the supernovae, and as particles bounce back and forth across that shock, it can accelerate them to high energies. So we think that protons and electrons get swept up in those shocks and accelerated to high energies, and that's where most of the cosmic rays in our galaxy come from. There's a relationship between how fast the shock is going and the spectrum of the cosmic rays that you get out. In the limit where the shock is very supersonic, that spectrum asymptotes to e to the -2. So when I say strong shocks from supernovae give e to the -2 spectra, that's what I mean. There's a formal relationship, which I do not remember offhand, but like subsonic shocks or shocks that are only slightly supersonic will give a somewhat softer power law spectrum, like maybe e to the -2.2, e to the -2.3. And yeah, there's an actual relationship between the speed and the index, but it's a really simple one. So this doesn't have to be true. This is just an example. You could make this e to the -2.5 instead, and it wouldn't really change anything about the example that we're about to do. But that's why that is the reason for my choice of it as an example. So the positron secondaries, their source spectrum is not e to the -2, is this softened spectrum of the original protons. So then if we ask, what is the steady state spectrum of these resulting positrons going to look like? If the positrons themselves are also in the diffusion dominated regime, we're going to get a spectrum that has an extra power of delta in it. It was just Q of E times e to the -delta. And if they're in the loss dominated regime, we're going to get a spectrum which is like either -3 plus delta. So the only point that I want to make here is that because the effect of both diffusion and the energy losses we've talked about is to soften the spectrum relative to the injected spectrum, we expect secondary particles to have systematically softer spectra than primary particles, just because the secondary particles essentially get to count this diffusion or loss softening twice. Once in going from the source spectrum, the primary particle to a steady state spectrum, and then again in going from the steady state spectrum, the primary particle to the steady state spectrum of the secondary. So our generic expectation is that the secondary particles will have softer spectra than primary particles. Which means that if you see a situation where a secondary particle has a significantly harder spectrum than you think is something that should be a primary particle, then that usually means that there's some important difference in their source spectra. So. Basically, the more steps you go from the original source spectrum, the softer you expect the spectrum to be. So if you see that a particle that you think is a secondary has a harder spectrum than a primary, it may also be a signal that what you're looking at is not a secondary, that there is a primary source of production of that particle. And this is in fact exactly what happens for high energy positrons. In AMSO2, we see that at high energies where you would, so we think positrons are secondaries, electrons are primaries. We think the electrons and protons are both getting accelerated in supernovae, but you see that at high energies, the positron spectrum is actually quite a bit harder than the electron spectrum. So that is a diagnostic that either there's something about cosmic ray propagation that we don't understand, that these equations need to be modified, or that you have some primary source of positrons out there with a hard spectrum. Okay. Stop at that. Okay. So that's basically what question?
Are there dark matter like showering mechanisms that lead to predominantly positrons specifically?
Good question. So the question was, are there dark matter showering mechanisms that lead to predominantly positrons? For most dark matter models, since they should be uncharged under the standard model, in most cases, you expect there to be equal numbers of electrons and positrons. That can still give a big overrepresentation of positrons relative to what you would expect from the standard model, since in the standard model, there are a lot more, in conventional physics, there are a lot more electrons than positrons. That said, it is possible to devise models where the dark matter is still uncharged under the standard model, but produce it where it carries like lepton baryon number. And so it produces like an excess of positrons that is compensated by like an excess of antiprotons rather than protons. So like, yeah, people have written down models like that where dark matter just loves to make positrons, but not so much electrons. Okay, so takeaway points from everything that we just did. The way that we think charged particles propagate through our galaxy is that they're diffusing through turbulent magnetic fields and simultaneously losing energy. Both of those effects, diffusion and energy losses, have a tendency to soften the steady state spectrum that we observe relative to the spectrum that you initially injected, but by different amounts, depending on what regime you're in. Even if you inject particles that have a delta function in energy, the steady state spectrum will be smoothed out to a power law with a cutoff. So we don't ever expect to see like just spikes in our, just like localized spikes in our energy spectrum for charged particles, but we can look for the charge cut, we can look for the sharp cutoff, and that can be a signal of something novel going on. And secondary particles, generally speaking, we expect to have softer spectrum than primary particles. So if you see something that you think is the secondary but has a very hard spectrum, that may be an indication of a primary source. Question?
Can you repeat this sharp cutoff?
Yeah.
This is sharp cutoff. I mean, even if I put in some kind of delta function, I expect it to be smooth both ways. So
okay. So yeah, so like look at this, the effect of the losses is only to smooth the delta function to lower energies, not to higher energies.
Oh, but I guess in reality, I guess we ignored the reacceleration here.
That's true. So yeah, but if with terms that I have not considered, it is perhaps possible to spare it in both directions. But if the losses are dominating over the other variations in momentum space, you can still expect there to be a pretty sharp drop corresponding to where the cutoff occurred. But yes, when I said you can still have a charge cutoff, I was thinking within the context of these approximations that we've done here. So that just came from this example, where if you're trying to get a delta function upon imposing a derivative, it means you've got a step function.
And can you just briefly talk about how this reacceleration might look? I mean, how strong is it? Or
I'm gonna pump that to later and send you some references, because while I have read some papers about this, this is definitely not my area of expertise. The paper that I mentioned earlier, this Yuan et al. 2017 paper, they argue that there's experimental evidence in the data for diffusive reacceleration, that you can't just ignore it. But I think my understanding is that you can get a good sort of like zeroth order description of the data just ignoring it, which is why I dropped it here. But to get the details right, you may need to include terms like that.
and
But usually we guess that it's a correction. But there have been studies like of whether you could get like a hard high energy positron spectrum through the acceleration. So like it's not true that in all possible models it's a negligible effect. The conclusion is mostly that you can't. Like it's really hard. So.
Perfect. And I guess I'm wondering if there's any kind of observation for any kind of sharp energy cutoff that we've seen anything anomalous.
Wait till next lecture.
Perfect.
There's definitely a fall off. The question of how sharp it is unclear, because of course when you're looking for a sharp cutoff, you also have to worry about just like statistical uncertainties and the energy resolution of your experiment.
So yesterday you were showing, yesterday you were showing the spectra, different spectra depending on whether dark matter relates into electrons, positrons, photons. So I guess this is obviously the injected spectra, not the spectra.
That was the injected spectrum. This is what happens to that spectrum post propagation. So, although I think usually yesterday I was sketching photon spectra, which won't be distorted in this way. But yeah, like if I have DMDM straight to E plus E minus, this is the most extreme example, then my injected spectrum is going to look like that. And we just argued that my spectrum after propagation is going to look like that. And you know, if I have something like if I have DMDM goes to mu plus mu minus, then the spectrum of electrons might look, then you know the spectrum of electrons will be somewhat broader because there's some distribution in the electron energy. So you know maybe my electron spectrum is like this. You know you can sort of say, okay, model this is a bunch of delta functions, take the sum. Then what you're probably going to get is some spectrum that looks like this after propagation. Okay.
Thank you.
So yeah, but the hope would be if you have something sharp like this, maybe your back and so if you think about what the backgrounds look like. Maybe your background from supernova acceleration looks like that over here. So you say, oh, this is great. This is very easy to distinguish. But then over here, the difference is that, maybe this looks like that. So you can look for a harder spectrum and you can look for sharp cutoffs. But there are uncertain, that's the other thing. You don't know the diffusion coefficient exactly. So your theoretical prediction for this probably actually looks like that. And your theoretical uncertainty on your background may look like this, right? So this is why this distinction is hard. But yeah, so these are the basic ingredients. That doesn't mean that you can do nothing. Like you can still set constraints, but it's not quite as simple as this case, which would, unless you're looking at a photon line, in which case you don't get this broadening, and then you maybe actually can do an analysis like this. Make sense?
Yeah.
Okay, so that's a good segue into what I want to talk about next, which is, okay, so that was the situation for charged particles. you'll see tomorrow that we can actually still set pretty strong constraints on dark matter annihilation and decay using observations of charged particles. But the limitations are always that there are significant systematic uncertainties associated with these associated with the propagation. And so as we get better observational handles on just propagation in the galaxy, so like astrophysical inputs, just how to charge particles move through the galaxy, that can potentially tighten constraints on dark matter annihilation or decay quite a lot, because it allows you to beat down these uncertainties. Okay, but so now let's turn to the case of photons and neutrinos, which travel in straight lines or travel along geodesic trajectories, and so we don't need to worry about this kind of distortion. So in that case, we are in the privileged position of not just having energy information when we look at our signals, but also having directional information, and we can look specifically at regions of high dark matter density and look for signals that are peaked in regions of high dark matter density and use that to try to distinguish signal from background. Okay, so the basic inputs here are, suppose we are given some 3D distribution of dark matter, which we either observe or model. And I want to know the spatial distribution. Spatial distribution and rate of photons or neutrinos coming from dark matter annihilating in that distribution. So our picture here is, we're over here at Earth. We have our eye or our telescope. Out here somewhere is a region of dark matter density. Annihilations are occurring in this dark matter density. So we'll look at the contribution from some little volume element, and then we're going to do an integral to get the signal from all the volume elements. Here on Earth, we usually can't tell where along the line of sight the signal came from. So what we'll be looking at is within some solid angle, how many photons do we see coming from this dark matter annihilation effect? I'm going to say photons throughout this, but everything here also applies to neutrinos.
Would we not use like a cosmic ladder just because there's a lot of uncertainty, or?
Yeah, good. So the question was, will we not use like a cosmic ladder just because of and is that just because of uncertainties? Yeah, so sometimes you have redshift information. Like for example, if you see a signal and you can see that the direction the signal is coming from happens to line up with the galaxy cluster at like redshift 3, whose distance you've measured through this kind of like cosmic ladder inference, then you can say, great, okay, the signal is coming from somewhere at redshift 3, as a good hypothesis. But a lot of the signals so are a few contributions. So there are a few issues. So sometimes you're not looking from a signal from a well-defined object, you're looking at like the integrated contribution to some isotropic background stuff. In that case, you can guess at the contributions to the known objects, but there may be other lower mass objects that also make strong contributions to your signal and that you can't actually see in other wavelengths. You make a model for your total signal, but usually you will not be able to infer, okay, this specific photon came from this specific point. Also, a lot of the observations that we do are at pretty low redshifts, such that you can't really use the redshift. Again, you may be able to say, okay, I saw a bunch of photons from that galaxy over there. I know how far away that galaxy is. That allows me to get a three-dimensional distribution of where the photons are coming from. But in general, you won't be able to say, like, okay, this photon landed at my detector, can I tell where it came from? All you know is, what direction, what angle it came in on stuff. Does that help explain? Yeah. So like sometimes, so you can usually have a three-dimensional map of your theoretical prediction, but the thing you actually observe is a photon hit my detector and it came from this direction with this energy. Okay. So let's suppose, so this is going to be a solid angle d omega that we look at. So I want to know within this solid angle, how many photons do I see? So I'll have a detector at Earth we'll say that this detector has an area A, and I want to know how many photons from the dark matter annihilation does my detector at Earth see coming in from this solid angle. Okay, so let's first just figure out how much annihilation is happening in this little volume, and then we can figure out how much we see. Okay. So the signal flux. So we want to consider the signal flux from a volume element. I'll call this dV. I'll say that it's at a distance r from my telescope. Okay, so I'll work in spherical polar coordinates centered at my observation. So my volume element is r squared dr d omega. Okay. So this is what we want. So, okay, so the annihilation rate within that volume so the rate is going to be n squared times sigma v. If we have two identical particles in the initial state, we'll have a factor of 1/2 here. And then we're going to multiply by dV. So this object here is rate per volume per time for annihilations per volume per time. We're going to multiply by dV to just convert it to a rate of annihilations per time. Okay. Okay. So now, and if we were doing for decay instead, we would say that this is just the dark matter. So n here is the dm number density. If we were doing this for decay instead, it would just be the dark matter number density times the decay rate times dV. Okay, so let's suppose one thing we need to know is how many photons or neutrinos is each annihilation or decay going to produce. Okay, so and that's the particle physics of our problem will tell you that. That was our step one, spectrum of photons and neutrinos or other particles produced per annihilation. So let phi be the spectrum of photons or neutrinos produced in terms of number of particles per element, differential element in E. So this is the spectrum per annihilation or decay. So this is like how step one injected result. So, okay, so the number of photons being produced is this produced per second, is this annihilation. So the number of photons being produced per second per energy interval is this annihilation rate times this phi of E value. So what fraction of those photons do we see at Earth? Well, we're going to assume that these particles travel at the speed of light and they spread out in all directions evenly from the original annihilation point. Even if the annihilation has some angle dependence, you're averaging over a very large number of particles in any dm volume. So overall, we can usually assume that the signal is isotropic. So then our telescope will see a fraction A over 4 pi r squared of all the photons or neutrinos produced at this point. So if I ask from this one volume element, what is the contribution to the number of observed photons at Earth, the d, dt, dB, this is going to look like n squared sigma b over 2 phi of E times A over 4 pi r squared. And so now we can move this dB to the other side, put an integral over it to integrate along all the volume elements along the line of sight. We said before, we're going to convert this into an, okay. I said I was just going to work with this d omega region. So we're going to just have a d omega here. And then this is going to convert into an integral of r squared dr times n squared sigma b over 2 times phi of E times A over 4 pi r squared. And if the if the only thing, so this is just integrating along the line of sight. If I also wanted to integrate over solid angle, then I would put another, then I would just integrate over the solid angle here. So if we were doing decay instead of annihilation, the only difference would be that instead of n squared sigma b over 2, we would replace this component with just n times the decay rate. Okay, is this good so far? So we can simplify this expression a bit. In particular, this R squared cancels out with this R squared. So this gives us a result that is, so we're going to have, if we assume that the cross-section doesn't depend on position, which is not always true, like if it's P-wave suppressed or Sommerfeld enhanced, the cross-section will depend on the velocity of the particles, and that can depend on where they are in the universe. But if that is true, then we can write this as Dn observed, unit energy per unit time, a solid angle on the sky as A 4 pi, and in fact, let's just pull the A over to this side as well. So this is per detector area now. So then we're going to get one piece, which is 1 over 4 pi and squared sigma V on 2 for annihilation, or 1 over 4 pi times m gamma for decay. And then yes, so sorry, let me go back a step. N does depend on positions. That was kind of the whole point. That we have some distribution of the dark matter density. I had better not pull that outside the integral. Okay, but so what we have for annihilation is that we get integral. We'll pull the pi at B out the front again. If we assume that this doesn't depend on position, we can pull this outside the integral. And so then this becomes E of R dr times n of R squared for annihilation, and d of R n of R for decay. We can do one other simplification because it's not actually the number density of dark matter that we measure, it's the mass density of dark matter. Like that's what tells us about its gravitational pull. So we can replace this n of R with the mass density of dark matter divided by the dark matter mass squared for annihilation, rho of NDM. But okay. Since that NDM is sort of part of the particle physics of the problem, we'll just pull this out the front. Okay. So then we see that we've separated this expected signal at our telescope into two components. This first part tells us about the particle physics of the problem. This is telling us about the cross-section. This is telling us about that injection spectrum that we computed earlier. This is telling about the mass of the dark matter. This slice is telling us about the particle physics. This piece, on the other hand, is just telling us about the distribution of dark matter density through the universe. So this is what we can hope to get at from the from looking at the gravitational pull of dark matter on visible matter. So these quantities here on the right-hand side are typically called, for annihilation, this is typically called the J factor. For annihilation, and it's sometimes called the D factor for decay. I should note, this is the question of whether you put the 1 over 4 pi at in the particle physics piece or the J factor piece is not a settled convention. So if you were looking at people quoting J factors in the literature, check whether they have defined it with or without the 4 pi. I know of at least one paper in the literature that had a nominal constraint that was a factor of 4 pi weaker than it should have been, and thus looked non-competitive with other constraints because they pulled numbers for J factor from another paper without checking what the 4 pi convention was. So I have seen both conventions in the literature. I have also seen like the factor of 2 in the annihilation piece being pulled into the J factor. So like just check which one is in use in the reference that you were using. Okay, So that's right. So the way that the searches for photons and neutrinos generally work is that you talk to stellar dynamicists who have made measurements of how the stars are orbiting around the area that you want to look at, or who have done gravitational lensing measurements of the mass density in that area, and you ask them to give you a model for what rho of R is. You plug that in, you work out your J factor, or you take their results for the J factors. You, as if you're a particle theorist, you do the particle physics side of the calculation. You put those two pieces together, and you compare it to the observations. So we're coming close to the end of this time, so I just want to say a couple more things. So first, throughout this, I have assumed there's no redshifting. You may have noticed. So yeah, I assumed that we could just use R as a parameter. I didn't worry about thinking about geodesic trajectories that are not just traveling in a straight line at the speed of light, now spherical coordinates. So what happens if you need to include redshift? It's actually pretty simple. So to include redshifting, there are a couple of things that we need to check. So the first is if I want to see particles with energy E as Z equals 0, then that means if they were emitted at redshift, then those particles need to have started with energy E prime equals E times 1 plus C. Okay, so our phi of E flux here is actually going to be phi of E prime. The other thing we need to take into account is phi of E equals dN by dE. So phi of E prime equals dN by dE prime. So there are two factors here. First, we need to convert the energy interval. So to convert into a quantity differential in E to a quantity differential in E prime, we're going to need to include a factor of dE prime by dE, okay? Multiplying phi of E prime. And since E prime is just 1 plus C times E, this factor is going to be just a factor of 1 plus C. The other thing that you need to take into account is if I injected a certain number of particles of like redshift 10, say, by the time, if I ask what's the contribution of those particles to the number density of particles in the present day universe, they will have been diluted by a factor of 1,000 compared to particles that were just injected, right? So also need to dilute injected particles by a factor of 1 plus C cubed. So what we end up getting in the end, so if we want to look at dN obs, so the number of observed particles with respect to energy, with respect to time, divided by the area of the detector, which I'll now call dA, and we can put in a d omega here as well. The expression that we're going to get, so we can replace the integral over R with an integral over dt, and then we'll replace that with an integral over redshift. So we're going to integrate from t today, from the time of emission to the time today. I'm putting the c dt. I'm putting in the c here just to be clear, but we're working in natural units, of course, so this is just one. This will replace our integral over distance, or integral over R. We're just going to integrate on how long it's been since the particle was emitted instead. We're going to replace our phi of E with the phi of E prime. We're going to multiply it by a factor of dE prime over dE so that we can get the dE in the denominator over here. We're going to put in a dilution factor of 1 plus E cubed, and then we're going to have our particle physics prefactors, which are similar to the non-redshifted case. For annihilation, but okay. Okay, so now it's a little bit, so this is a valid result, but it's often easier to write this as an integral over redshift, not an integral over time. So if we want to do that conversion, we can note that h of z, the Hubble parameter, so this is 1 over a dA by dt, we can rewrite that in terms of the redshift, so that's d log a by dt. Since a, the expansion factor, scales like 1 over 1 plus c, we can rewrite this as minus d log 1 plus c over dt. So that's minus 1 over 1 plus c dc by dt. So that means that we can convert, so to convert this integral over dt into an integral over dz, we need to multiply by a factor of minus h of z over 1 plus c dz. So we can rewrite this result in terms of a z integral as 1 over 4 pi integral of dz from the present day z equals 0 to the earliest redshift that we're taking into account, times 5 at e prime equals e times 1 plus z divided by h of z. Oh, wait, hang on. Did I mess up the h of z placement? Yeah, sorry. This should be messed up here, right? dt should be, 1 over h of z dt. Sorry about that. Have a 1 plus c cubed back to here, and then this particle physics factor inside the integral. So when we're talking about redshift, we usually don't talk just about simple J factors because now the energy spectrum can't be taken outside the integral because it varies because it's evaluated at a point that compares that depends on the redshift. But this is the appropriate generalization of your signal to the case where there is redshifting. Okay. So that is basically what we need to know for step 2 of how we get from our signal how we get from the spectra at injection to the spectra that we see at our detectors, both for charged particles and for neutral particles. So next time I will start out by doing a quick estimate of the signal size, telling you a bit about, but for this kind of calculation, you can do this yourself, and doing a quick discussion of backgrounds, and then we'll jump into what the constraints look like. And at this point, you should now have all the information needed to understand the constraints. Thanks very much.